Okay, good afternoon, folks. This is our lecture 2 on advanced power electronics. If you were not here last time, I would encourage you to take a look at the material that is already uploaded on Blackboard, the syllabus of the class, as well as the schedule of the class. As I mentioned last time, we are going to be taking attendance not this week, not next week, starting the third week of classes because there are some international students traveling. Also, starting the third week of classes, we are going to have, every week we are going to have at least one homework assignment or one quiz. So basically your first homework assignment is due 1.5 weeks or 2 weeks from today. And it's not even posted on Blackboard, so there's nothing to worry about. What we did last time was we looked at, last time and today probably, and maybe a little bit of next time, we are going to be reviewing some of the classic power electronic converters. Some of you have already been exposed to this, these kind of converters. So just bear with me. I just want to make sure everybody's on the same page. So in the future, when we refer to a particular converter, we know what we are discussing. The converter that we analyzed last time was the buck converter. It is called the step-down converter because the output voltage is a fraction of the input voltage. So the schematic of the buck converter is here. On the left-hand side, we have the source. Then we have a switch over here, and a diode, and an inductor, and a capacitor. So we analyze this. The command that is applied to the switch is like an on-off kind of a signal. On means the switch is conducting. It's like a short circuit. Off means obviously the switch is off, open circuit. And as it turns out, the voltage transfer ratio for this topology turns out to be V out over Vin equals a D, which is this relationship over here. Then we looked at some of the waveforms, how to design this converter in terms of finding the right value or the right size for the inductor and the capacitor. And we came up with these two expressions. One of them is here. So this expression is used to find the right size for the inductor. And always go 20% or maybe 50% beyond what this suggests. So if you do the math and the right-hand side of this inequality is like, 20 or 25 microhenries, go with 40 microhenries, just to be on the safe side. Also for the cap, remember one of the assumptions was the capacitor is too large or the voltage of the cap is almost constant, and we ended up with this expression over here. So the duty cycle is known, the value of the L, the inductor is already determined, so you have to design L, then design the capacitor. Frequency is known, and delta V out over V out is basically the percentage of the ripple for the output voltage that the customer tells you. For instance, the ripple should be plus or minus 1% or 2% or whatever it is. So you can actually plug in that number. Remember, delta V out is the peak-to-peak ripple in the output voltage. All right. So the highest amount of the output voltage minus the lowest amount of the output voltage. All right. So if you look at the topology for if you look at the schematic for this topology, so we are still continuing on the buck converter. Let me make it a little bit thinner. So if you are curious about how did they come up with this topology, here is a short description of how. All right, so we analyzed this and we realized that the output voltage is D, which is the switching duty cycle, times the input voltage. This is as if we say, for instance, I have an input voltage which is 12, and I only need 50% of that on the output side, which is 6 volts. So D is like a percentage of the input that you need on the output side. So technically I can draw these waveforms. So this is my input voltage, which is a constant DC signal. And on the output side, I only need, for instance, this portion of that. All right. So let's say the output voltage is 50% or 40% or 30% or 25% of the input voltage. You can see these are both DC signals. And what I can do is I can say I can manipulate the input voltage to be a waveform like this, to be converted to a waveform like this. All right. So using the input voltage, we are going to see how we can actually generate this red signal. That this red signal, sometimes it is following the input voltage, and sometimes it's actually at zero level. And we can construct the signal in a way that the average value of the red signal is the output voltage. So the average value of red is V out, basically. So in order to take the average value of a signal, we can use a low-pass filter. And as it turns out, this inductor and this capacitor are working like a low-pass filter. What about this red square-shaped signal? This red square-shaped signal is actually here. Let me call it Vx. All right. So Vx is the reverse of the voltage that appears across the diode. And this Vx is applied to a low-pass filter, and the DC component of Vx, which is what we need, appears on the output side as the output voltage. So how is Vx constructed? So look at mode 1. It always goes back to this, so I have to do this always manually. Remember, in the first mode, the switch was on and the diode was off. So if the switch is on, it's like there is a short circuit across the switch. Diode is off. We don't have to worry about it. And in that case, Vx and Vn are the same. So basically, Vx is the same as the input voltage. Now, the other mode that we had, which was mode 2, during which the switch was turned off, and therefore the inductor turned the diode on. Now, if you look at Vx, switch is off, open circuit, don't worry about the switch and the input side. Diode is on, it's like a short circuit, it's an ideal diode, so Vx is 0 basically. So that signal that we were trying to implement, which was sometimes following the input voltage and sometimes following 0, which was labeled to be Vx, is basically constructed using this switch and this diode and following the basically switching pattern. So technically Vx which is this signal. So this is one period, this level is V in, and this level is 0. So technically I can say Vx is the input voltage multiplied by the gate signal. Or the command that is applied to the search, assuming that this is a mathematical signal, so I have to define it in this way. The gate signal is 1 when the switch is desired to be on, and it is 0 when the switch is desired to be off, basically. Oops. Okay? So this signal is generated by the controller. There is a DSP, there is an analog controller somewhere that is making this signal. This signal, which I call it the gate signal or the command to the switch or the switching command, whatever it is, it's a periodic signal with a period of capital T. And we defined the duty cycle last time for the first segment of the period, which is duty cycle times T, or that portion, it is on or 1, basically, a logic of 1 or a numerical value of 1. And then for the remaining, it is 0. So we have this signal applied to the gate of the switch. Okay? And then the switch and the diode operate like an amplifier or like a multiplier, basically. So they multiply the signal by the input voltage, and the result appears across Vx, which is almost the same signal, just amplified or multiplied by the value of Vn. And then we have a low-pass filter of an L and a C, which basically obtains the DC value of this signal. And that is actually our output voltage. So some people call this topology a chopper. The reason is we are chopping off part of the input voltage. We are keeping part of it, and then we are chopping part of it out. And so we are keeping part of it, which is the high values, this portion, for instance, and then we are chopping part of that basically out. So some people call it a chopper. Some people call it an amplifier. The reason that they call it an amplifier is a weak signal like this, the gate signal, is for instance 0 and 5 volts or 0 and 3 volts or whatever it is being amplified to 0 and Vin. So we are actually doing a multiplier here as well. So if you hear somebody call it a chopper topology or an amplifier, this is why these terminologies are where they are coming from. Any questions on the Bach topology? All right, so it's pretty much straightforward. As I said, every laptop, there is at least one Bach topology, at least one in every laptop. There is at least one Bach converter in any cell phone. And they are pretty much a lot of places, okay? The next topology, yes?
You said that the LC will act as a filter also.
A low-pass filter, right.
So when we design the converter, do we care about the LC value so that the filter, designing a filter way, or we do...
Okay. So the question is, this LC operates like a low-pass filter. When we are designing L and C, do we care about the features of this low-pass filter? Actually, these features are embedded when we had those two equations last time, that L has to be greater than something and C has to be greater than something. So this red equation over here and this red equation over here, these two. Those features are actually embedded here. So once we follow this procedure, we are guaranteed that our LC filter is giving the DC component of Vx, and it is eliminating the AC harmonics that are actually in Vx. So that was a good question. So yeah, they are already embedded in here, in these two equations. Any other questions?
Would you be concerned about resonance?
Resonance of L and C. If you do a good job, no. But at the same time, the resonance is dependent on your load. On very light loads, you may actually see a little bit of a resonance. But at the same time, at light loads, you have to be worried about some other stuff. For instance, going from continuous conduction mode to discontinuous conduction mode. Generally speaking, no. In a second order system, there are easy ways to actually damp down and do a good job in terms of L and C selection, so you wouldn't have any resonance. But like if your converter has two L's and two C's, you realize sometimes it becomes a challenge getting rid of that resonance. But usually your resistor is acting like a damping factor. So if you have a large resistor, in other words, you're consuming a lot of power, resonance wouldn't happen. Other questions?
So we got, we thought that capacitor should be large to reduce the ripple.
Right.
So how large can it be? Like considering inductance say greater than 25, so we take 40 microhenry as inductance.
Right.
So then what should be the capacitance be? Large capacitance.
So we follow this equation. The numbers that you are going to get is there is a we can have a numerical example, but usually a switching frequency of 100 kilohertz gives you an inductor of about, for instance, 20 microhenries, maybe 30, 40, 50, and a capacitor of about maybe 100 microfarads. So when we said large, we didn't mean hugely large. So 100 micro for a switching frequency of 100 kilohertz would do the job for us. So it's not like 10 farad or something like that. So remember, switching frequency is important, and the duty cycle is important, as well as the value of the load. Like in the top one, L has to be greater than 1 minus duty cycle times the value of the load. So if you have a very large load, that demands for a very large inductor as well. I'm hesitant about giving you a numerical example because it's a little bit boring, to be honest. What I can do is I can actually scan my numerical example and post it on Blackboard. So I had a numerical example, but it's just following these two equations, so it's not that challenging. All right, so let's move on to the next DC to DC converter, which is the boost topology. So as the name suggests, it is boosting up the voltage, the input voltage. So the output voltage is larger than the input voltage in terms of value. Sometimes called a step up topology because it is a stepping up or boosting up the voltage. The applications could be, for instance, you have a camera. In a camera, if you want to use the flash, the battery that you have in a camera is about like 5 volts, whatever. Let's say you have lithium-ion batteries, it's about 4 volts. But the flash works with, like, for instance, 100, 200 volts. So you have to boost up the battery voltage to a much larger voltage to charge a tiny little capacitor in there. So when you click on, taking a picture, that energy in that capacitor is released in the flash, so you have a, flash of light, so you can actually take a good picture. So most of the times in cameras, if there is a flash, which is in all cameras almost, so there is a boost converter doing the job for you. It's a tiny converter. Other examples could be when you have a solar panel and you want to tie it to the grid, the voltage of the panel is usually about, for instance, 30 volts. Or maybe you have a series of panels, connected in series. But usually you boost up the voltage to a voltage that is higher than the peak value of the grid power, which is 110 times the square root of 2, and then use an inverter. So a lot of, in the solar applications, right after the panel, there's a boost converter, basically. So the schematic looks like this. All right, as you can see, we are using the same components that we used for the buck converter. We still are using one inductor, one capacitor, one switch, and one diode. And as I said before, we are going to talk about semiconductor devices later, but this switch is usually a power MOSFET, an N-channel power MOSFET. And obviously, there is a gate signal that is turning this MOSFET on and off. Notations about the boost converter is the inductor is actually placed in series with the input side. And remember, the current of the inductor is continuous. That means the input current of this topology is continuous, which is a good thing, actually. Whenever you are drawing a continuous current from a source, that is preferred to whenever you are drawing a discontinuous current from a source. So we made a bunch of assumptions when we were analyzing the buck converter, and those assumptions are also being made right here. For instance, one assumption was that we are looking at the system under steady state conditions. Remember, a steady state was, on average, the voltage across the inductor is 0, or on average, the current of the inductor is constant. or on average the current of the capacitor is 0, or on average the voltage of the capacitor is constant. So those are the steady state requirements. Or, for instance, if I look at the inductor current at the end of the switching period, it is the same as the inductor current at the beginning of the period, or basically on average, as I said, the inductor current is neither rising or falling. It's actually following a constant value on average. So this was one condition. There is another condition, which is we are analyzing the system under continuous conduction mode. Continuous conduction mode, and that was determined by the form of the current of the inductor. So technically we are assuming that the minimum value of the inductor current is positive. It never stays at 0 level. So that's another assumption. The other assumption is the capacitor, the output capacitor is large. Again, largeness doesn't mean we are talking about hundreds of farads. Largeness is in respect to the switching frequency. If our switching frequency is around 100 kilohertz, C is like about 100 millifarads, microfarads. So C is large, or in other words, the output voltage is almost DC, or the ripple in the output voltage is neglected, basically. And the other assumption was we don't have any losses in the system. We don't have any internal resistance, for instance, for our switch or for our capacitor, nothing. There are ideal components, or the input power is the same as the output power. So these are the 4 typical assumptions that you make before analyzing a converter. And your question might be, oh, what if my converter is not ideal? So once you go through the simple route of everything is ideal and figure out how the converter operates, you can come back and tweak your simulation or tweak your analysis in a way that, okay, now let me consider the internal resistance of, for instance, the inductor, and see what happens. The switching pattern is also assumed to be the same as before. It's a periodic signal with a period of T. And duty cycle is defined the same way that it was defined before. And so technically we have 2 modes of operation. So again, remember the switching pattern. Is the same as we assumed it is for the buck converter. All right, something like this. So on, off, on, off, on, off. And D, lowercase d, which is the duty cycle, is determined by the on time of the switch divided by the overall period, by the overall switching period. So similar to the previous converter, we have 2 modes of operation. Mode 1, during which the switch is on. So technically we label this mode to be mode 1. And then mode 2. So according to the switching pattern, in this mode, mode 1, the switch is on, okay? So technically, let me redraw the diagram. So this is my switch that is on now. Okay, so this is how the circuit looks like. We have to figure out what happens to the diode By turning the switch on, basically, we can see that whatever output voltage that we have here appears here as well. All right. And assuming that, let's say this is the very first time you're analyzing this converter, you don't really know what the polarity, the correct polarity for the output voltage is, you can make an assumption like this, that the polarity is in a way that the top plate of the capacitor is positive and the bottom plate of the capacitor is negative. In that case, following that assumption, the diode is reverse biased because we are applying a negative voltage from the anode to the cathode of the diode. Okay, remember, diode voltage is always measured from anode to cathode, and in this case, it is negative V out. And assuming that V out is positive, we don't know yet. Later on, we have to double check. But assuming V out is positive, negative V out is negative, therefore VD is negative, therefore diode is off. All right, so pretty much similar to the previous converter. When the switch is on, the diode is off. And what happens is basically we are energizing this inductor using the source. That's all that is happening. And all we care about for now is the voltage drop across the inductor. Okay? So VL is nothing but VN. Okay, so we turn the switch on, kind of like the previous case. We expect the inductor current to rise and basically ramp up linearly. And in this case, VL is VN. Now let's take a look at the second mode, mode number 2. We turn the switch off, similar to the analysis that we had for the buck converter. The switch is turned off. The current of the inductor is non-zero and it has to be continuous. So it has to flow through somewhere. Before it was flowing through the switch. Now the switch is blocked and it's like an open circuit. Therefore it has to push the diode to turn on. So diode turns on. By the inductor. So the inductor is in charge of turning the diode on, and now our diagram looks like this. Switch is open. Okay, something like this. Again, all we care about for now, as long as the voltage transfer ratio is concerned, is the voltage that appears across the terminals of the inductor. And this turns out to be Vin minus Vout. You have to just write a KVL around this outer loop. So VL is Vin minus Vout. From our previous experience with the Bach topology, in one mode VL is positive, in one mode VL is negative, and on average it should be 0 basically. If the previous mode VL was positive, which was Vn, in this mode VL should be negative. The indication is the output voltage has to be greater than the input voltage. Alright, so the volt-second balance for the inductor says, so I forgot to mention it last time. So this thing that we would say the average value of VL is 0 is called the volt-second balance. All right, volt-second is when we multiply voltage by time, which is in seconds, or basically when we are integrating the voltage basically. So this is happening from 0 to dt. This is happening from dt all the way to the end of the period. So I would say Vn from the first mode times the duration of the first mode plus Vn minus Vout, which is in the voltage on the inductor during the second mode, times the duration of the second mode. Should be 0. So T comes out, so the voltage transfer ratio is independent of the T, and in the end we are going to end up with this expression. All right. So remember, these is still our duty cycle, a number that is varying from 0 to 1, ideally. And if you look at this, there are two conclusions that you can make. One is the output voltage is always positive. The other one is the output voltage is always greater than the input voltage. So the output voltage is positive was one of the assumptions that we made earlier. In the first mode, when we turned the switch on, we looked at the voltage drop on the diode, which was negative Vout, and we said if the output voltage is positive, therefore the diode is off. So this is actually, confirming that the output voltage is actually positive in the polarity that we assumed. The other one is, Vout is greater than Vn here. The other conclusion is that the output voltage is greater than the input voltage, which actually agrees with the title of the converter, which is the boost converter. Okay. Now, similar to the Bach topology, if you are interested in, for instance, bunch of waveforms, that was, for instance, the switching pattern. Okay, now if I look at the voltage that is applied to the inductor L, in the first mode it was Vn, which is positive. In the second mode it was Vn minus Vout, and because Vn is less than Vout, it is negative. And on average it is 0. And the same pattern continues. Something like this. So this level is Vn, and this is Vn minus Vout. And for instance, the inductor current looks exactly like the inductor current of the boost of the Bach topology. First mode, the inductor current is being energized. Second mode, it is being de-energized. And so on and so forth. Something like this. So in the first mode, it is being energized by the source, the DC source. In the second mode, it is de-energized by the output voltage, so we are sending energy back, or basically to the output side, to the capacitor side. Now, we can do the same analysis and find a bunch of expressions in terms of what is the expression for I max, what is the expression for I min, what is the expression for the average value of the inductor current. I'm not going to go through the details of those. I'm just going to write them over here. But I'm pretty much sure you're familiar with those, and you can actually take a look. I will scan my detailed notes and post them on Blackboard if you're interested in taking a look. For instance, the first obvious one is delta L. Which is I max minus I min basically. Okay, we can look at the first mode and describe it in a sense that it is Vn, the voltage on the inductor, over the value of the inductor times the duration. Or second mode, again, remember delta IL is always positive because I max is always larger than I min. So I have to write it the positive voltage across the voltage across the inductor multiplied by -1, which is V out minus Vn, over L times T minus dt, which is the duration. So these are two identical expressions for the peak-to-peak ripple of the inductor current. And again, if you look at the left and right hand side, you can again conclude that V out over V in is 1 over 1 minus D. Now, in terms of average value, for the Bach topology, it was easy because the average value of the inductor current was feeding the load resistance. Here, actually, the inductor is on the input side, so the average value of the input current, of the inductor current, is the same as the average value of the input current. All right, which is Pn over Vn. Okay, it's a DC system. Power is basically just DC voltage times average value of the current, and Pin is the same as P out. And P out is V out squared over R. And at the same time, I'm not going to write it over here, we know that V out is Vn over 1 minus D. So once we combine these two equations, we can actually have a description for the input average value of the inductor current, which is also the same as the input current, in terms of the load resistance, the value of the duty cycle, and for instance, the value of the output voltage or the value of the input voltage. Whatever we want to eliminate, we can eliminate combining these two equations. In terms of I max and I min, and so by the way, this is the same as I max plus I min over 2. This comes from the fact that the inductor current is a symmetric triangular waveform. It is following a straight line when it is ramping down. It is following a straight line when it is ramping up. So it's totally symmetric. So on average, it is basically the average value between its maximum value and minimum value. So once we combine these two lines of equations, we can end up with expressions like this. Let me see if I have the expression somewhere. Oh, here it is. For instance, the minimum value of the inductor current is, now here everything is appearing in terms of V in, not V out. It doesn't matter, we can reflect it to the other side. Okay. And obviously we have something similar to this for I max, and this also gives us a hint in terms of what is the right value for the inductor current. Remember, for CCM, continuous conduction mode, we need to make sure that I min is positive. Therefore, the inductor should be larger than this expression. It's a little bit more complicated than what we had for the Bach topology. D is multiplied by 1 minus D squared. So it's not really easy to look at it and say under what conditions this expression is maximized. But remember F, which is the switching frequency, which is 1 over T, appears here as well in the same fashion that appeared in the Bach topology. So if we push up the switching frequency to higher values, the right-hand side of the expression gets smaller, therefore we'll require a smaller inductor. We have a numerical example here which might actually be worth sharing with you guys. Let me talk about it. Before that, let me just talk about the capacitor and then we get to here. So I'm just going to write the equation that we need for the cap. So in order to find this equation, we have to follow the same procedure that we followed for the Bach topology. We have to find the current waveform of the cap. Remember, on average, it's supposed to be 0, the current of the capacitor. Sometimes the cap is getting discharged, sometimes the capacitor is getting charged. And then, for instance, we look at the discharge period and look at delta Q, the amount of electric charge that comes out of the capacitor, and find the ripple of the cap. I'm not going to go through it, but anyway, this is the final expression. All right, something like this. So it's a little bit simpler than the Bach topology. It's only dependent on the value of the duty cycle, the load resistance, the switching frequency, and delta V out over V out is the normalized value in percentage of the ripple in the output voltage, like 1%, 0.5%, something like that. Okay, now let's take a look at a numerical example. So any questions, by the way? All right. So no questions. So for the boost converter, we have this information available. One is that the switching frequency is 50 kilohertz, which is usually lower than what it is supposed to be in a practical converter. The load resistance is 50 ohms. The input voltage is 12. The inductor is 70 microhenries. And the output voltage is 15. Okay. So the first question is the converter operating under continuous conduction mode? And please remember, even if it is not asked to do that, you should always ask it from yourself, because the entire analysis that we made is only true. All the equations that we have are only true if the converter is operating under continuous conduction mode. So whenever you're analyzing a converter, first thing that you have to make sure of is it operating under continuous conduction mode? So part A is asking about CCM. All right. And part B is asking about something else that we are going to talk about. All right, so let's look at part A. So is it operating under continuous conduction mode? Obviously, I have to find the minimum value of the inductor current and see if it is positive. If it is positive, then we are good. But in order to find the minimum value, I have to make the assumption that we are under CCM. So first we make an assumption that you are operating under CCM, and then later on you see if that assumption is violated or not, basically. So first I am assuming that yes, assume yes. All right. The reason that I'm making this assumption is all the equations that I have are only true if this assumption is correct. So I'm assuming that yes, it is operating under CCM. Therefore, I can find the duty cycle. So I have the numerical value for the output voltage, which is 15. The input voltage is 12. Therefore, the duty cycle is 0.2. Under the assumption that the converter is operating under continuous conduction mode. All right. Now, in order for the minimum value of the inductor current to be positive, either I have the expression, for instance, up here, and I just make sure it is positive. I just plug in all the numbers and make sure it is positive, or I can do something similar, which would be make sure that the inductor is larger than this expression, okay? So let's look at this. I'm just going to see okay, the duty cycle is given to be, or we just found it to be 0.2. The load resistance is 50. And this is twice 50,000. So this turns out to be 64 milli. And you can see the inductor is 70. So good. The inductor is larger than 64. 70 is greater than 64. Therefore, you are in business. You are in the continuous conduction mode. Okay. So remember, whenever you're analyzing a converter, first thing that you have to make sure of is this converter operating under continuous conduction mode? And it is. Now, part B is actually making it a little bit more challenging. Let's say we are trying to generate a variable output voltage. Right now, it's 15, but let's say the customer comes back and say, I want my output voltage to be variable. And they say, okay, easy. In order to have a variable output voltage, you can have basically tweak the value of your duty cycle, increase it or decrease it, and therefore your output voltage is going to increase or decrease. But then you have to be careful about violating that condition that L has to be greater than that expression. So that's actually part B. He's asking about find an output voltage range where the converter does not operate in CCM. Okay, so we are just curious, okay, if I'm trying to mess around with the value of my output voltage, under what conditions I am violating this CCM requirement? Okay, so the boundary between CCM and DCM is where L becomes equal to D times 1 minus D squared times R divided by twice the frequency. So this is like a boundary. This is the boundary between the CCM and DCM. Okay, so let's just put the numbers. So I just say, in other words, d times 1 minus d squared should be equal to 2 times L times F over R. Okay, so I have L, I have F, I have R, and once you do the math, it gives you 0.14. All right. So once I solve this simple, third order equation for the duty cycle, I will get 3 answers of this 0.428 and 1.325. Obviously, the third answer is not a good correct answer because the duty cycle is supposed to be less than 1 and larger than 0. And this is giving us a duty cycle that is more than 1, which is unacceptable. So this one is already automatically out. All right. So if you want to visualize this, I'm just going to draw it over here. I am drawing d times 1 minus d squared over times R over twice the frequency. I'm drawing this thing. Everything is fixed except for the duty cycle. So this is versus d. It looks like something like this. All right. Now, if I just draw this, which is the right-hand side of that design equation, it looks like this. And remember, L has to be larger than this. And L is actually here, the value of L. So we have 2 cross points, basically. And these cross points happen to be these 2 numbers that we found, which is 0.247. And the other one is, my scale is not very good, but this is 0.428. All right. So if we are in this region, if we select the duty cycle between these 2 numbers, L is not greater than d times 1 minus d squared times R over twice the frequency. And therefore, we are not in CCM. So in this region, we are in DCM. But outside of this region, like between 0 and 0.24 or from 0.428 to 1, L is larger than that expression. Therefore, we are in CCM basically. Okay? So we have found a range for the duty cycle that actually tells you if you are within that range, you are not in CCM. So all I have to do is just find the corresponding output voltages because part B is asking about find an output voltage range, not a duty cycle range. So I just call this one to be D1 and then D2. Okay, so D1 is 0.247, and therefore the corresponding output voltage would be input voltage was given to be 12, I believe. Yes, 12. So this gives me 15.931. All right, and then D2 this gives me 20.987. All right, so something like this. So the range that we were looking for is between these two numbers. So this is the DCM range. So if you are required to generate an output voltage which is between 15.9 and 20.9, you are operating in DCM. V out over V in equals 1 over 1 minus T does not hold anymore. Still you are boosting the voltage, no problem, but that equation doesn't hold. But outside of this range you are fine. You are operating under CCM, like from 0 to 15.9 and from 20 point, not from 0 to 15.9, from 12 to 15.9. And beyond 20.9, you're fine, you're operating under CCM, and all of the equations that we have analyzed, they all hold. And you can go back and check your answer with the very voltage that we were supposed to generate. Remember at the beginning, our output voltage was supposed to be 15, and our conclusion was that under this 15 volts of output voltage, we are operating under CCM. This is where we concluded here. And now you can see that that is correct. 15 comes out of this range, basically. 15 is smaller than 15.9, so you are working under CCM. So this was a numerical example of the boost converter, because it's a little bit more complicated, because the factor of D times 1 minus D squared appears in it. Just a note about theoretical and practical values for the duty cycle. Like here we are saying that the duty cycle could be any number between 0 and 1, or 0 and 100%. But practically, there are limitations for the duty cycle. One is basically going to the discontinuous conduction mode. Practically, we do not like duty cycles that are, for instance, less than 10% or higher than 90%, because you may go to the discontinuous conduction mode, or things may get actually a little crazy for all of these converters that we analyze. Or considering that practical limitation, or we are going to get a lot of ripple. Considering that practical limitation, here I'm saying that the output voltage is larger than the input voltage. So theoretically, I can, for instance, use a 12-volt source and generate 12 million volts, which is practically I cannot, because there's going to be a lot of losses, there's going to be a lot of ripple. So with the boost converter, let's say if the duty cycle is 90%, highest practical value that you can choose, therefore your output voltage could be 10 times larger than the input voltage. For instance, from 12 you can go to 120. If your objective is to convert 12 volts of DC to 12,000 volts of DC, one boost converter cannot do it for you. Theoretically it can, but practically it cannot. So you have to cascade a bunch of them in series, or choose another topology, basically. So remember, what we write down here as a mathematical thing may not actually happen in theory, because there are other limiting factors. For instance, the ripple. For instance, going to discontinuous conduction mode. For instance, having to choose a very large inductor or a very large capacitor, things like that. So always remember, a good practical range for the duty cycle is between 10% to 90%, or even 20% to 80%, something like that. All right, any questions on the boost converter? All right, so there is one last converter in this category that we are going to analyze even brieflier than buck and boost, which is called the buck boost converter. So let's take a look at that one. Okay, so the name, as the name suggests, it's sometimes like a buck, sometimes like a boost. So it's a buck boost, and the topology is like this. Okay, something like this. Several observations. We are still using the same components: one switch, one diode, one inductor, and one capacitor. However, there is a difference from this converter from the other two converters that we analyzed, and that is, I'm sorry, this is the input voltage. The polarity of the output voltage is reversed. We are going to see why, and so I assume that this is the right polarity for the output voltage, and later on it turns out that it is the correct polarity. But please remember, the polarity is in a way that the positive terminal of the capacitor is in the bottom and the negative terminal of the capacitor is on top. This is opposing the other polarities that we saw earlier for the buck converter and the boost converter. Like in this converter, if I assume that this is the ground node, the negative terminal of my source is connected to the ground as well as the negative terminal of the output voltage. For the buck converter, for the boost converter is the same. If I assume that this is the ground node, the positive terminal, the negative terminal of the input voltage as well as the negative terminal of the output voltage are connected to the ground. So the input and the output have the same ground. Here, if I assume that this is my ground node, then you realize that the negative terminal of the input voltage is connected to the ground, but the positive terminal of the output voltage is connected to. So we are actually going from a positive voltage into a negative voltage as our output voltage. So sometimes it's considered a disadvantage. Sometimes it is considered an advantage. Okay, now let me talk about the advantage now. Presume, so the buck converter and the boost converter, like presume you have a, for instance, battery here, which is 20 volts, and you have another battery here, which is 5 volts. Okay. And they have the same ground. And you want to transfer, energy from the left-hand side battery to the right-hand side battery. So you can say, okay, they have the same ground. I can use a buck converter to, for instance, transfer it. Or if you want to do the opposite, if you want to transfer power from the right-hand side battery to the left-hand side battery, you can use a boost converter, okay, to do the job. So here we can use, if the power flow is from this direction to the other, you can use a buck. If it is in this direction, you can use a boost. But the question is, what if your batteries are connected to each other in a string? Something like this. They don't have a common ground anymore. The negative terminals are not connected to each other anymore. You cannot use buck, you cannot use boost, but you can use buck boost basically. So you can use, I'm just going to redraw this buck boost over here. Or something like this. So if your batteries are connected in series with each other in a string of cells, you can use a buck boost converter to transfer energy from one cell to the other. And where do we need that? For battery charge equalization. So when you have a long string of batteries, sometimes some of the cells are overcharged, some of the cells are undercharged, and you need an equalization mechanism to make sure that those cells that are overcharged can transfer their energy to the cells that are undercharged. So for instance, one solution would be using a buck boost topology. So this portion is basically a buck boost converter. Okay. And the way that I drew it over here is you can get energy from the top cell and deliver it to the bottom cell, and you can reverse the topology. All of these converters are, by the way, bidirectional. In the end, we are going to learn about it. And then you can actually make it bidirectional to do the opposite flow of power. So this one, what it does is it takes energy from this one and delivers it to the bottom cell. So if the top cell is overcharged, you can get energy out of it and send it to the bottom cell that is, for instance, undercharged. So the fact that they don't have a common ground sometimes helps us, sometimes it doesn't. So just be very aware of that. And by the way, in some of the books, they are using this polarity that I have assumed, which is we already know the output voltage is reversed. Therefore, we don't have to worry about the negative sign in all of our equations. We have already reversed the polarity of the output voltage. In some of the books, they assume that this is the polarity for the output voltage. And then in all of the equations, there is a negative sign appearing. So in order to not worry about that negative sign, I just don't do this. But please be careful when you're opening a book and you're looking at a bunch of equations for the buck boost topology. Take a look and see what is the convention that they are using. Have they already reversed the polarity and all of these equations do not require a negative sign? Or they have not reversed the polarity, therefore you have to include a negative sign in all of the equations, basically. All right. Any questions so far? All right. So we are going to take a brief look at this topology. So again, we have those assumptions that we made earlier, like the converter is ideal. There are no losses in the system. We are analyzing the system under steady state conditions. We are analyzing the system under continuous conduction current. Also, the output capacitor is large in a sense that the output voltage is almost a constant voltage. So those four assumptions are always holding, or we are assuming that they are holding. And the switching pattern is the same, a periodic signal. Sometimes at the beginning of the cycle, it is 1 or true or on, indicating that the switch should be on or shorted. And then for the remaining portion of the switching period, it is off or 0 or false, meaning that the switch has to be off, basically. By the way, I think I did not highlight the polarity of the current here. So remember, when we were talking about the boost converter, this is IL, basically. It is coming out of the source. And here, it is in this direction. And we always follow the passive sign convention, so the current is flowing from the positive terminal to the negative terminal. Okay, so mode 1. So the switch is on, and we are going to see that the diode is going to be off. So let me draw this mode. I don't know what's happening to the diode yet, so I'm just going to draw it. All right. So we don't know what's happening to the diode. We have to look at the voltage that appears across the terminals of the diode and then make a decision. Remember, the voltage of a diode is always measured from its anode with respect to its cathode. So if you look at the outer loop, the diode, the voltage that appears across the diode is negative Vin minus Vout. And assuming that Vin is a positive voltage, our source is a positive polarity source, and Vout, in the polarity that we have assumed, it is also positive. All of these negative Vin minus negative Vout is negative. Therefore, diode is off. Now, I just assume that output voltage is positive in the polarity that I've assumed. That in the end, I have to actually make sure that that assumption is a correct assumption. So similar to the other two topologies, as soon as we turn the switch on, there is a negative voltage applied to the diode, which forces the diode to be reverse biased and therefore to be off. Now, what about the voltage drop across this inductor? It is the same as the input voltage. Okay. So in this mode, we are applying kind of like the boost converter. When the switch is turned on, Vn, which is our input voltage, is applied across the terminals of the inductor. It energizes the inductor. The current of the inductor ramps up linearly. And let's take a look at the second mode. Okay, so this is the third time that we are making this argument. As soon as we open up the switch, the current of the inductor is non-zero, and it has to be continuous. So one conduction path for the inductor has been blocked. The inductor is looking for another conduction path, which would be the diode. So basically, it pushes the diode to turn on. So diode is on. So in all of these topologies, it is the inductor that is forcing the diode to turn on in the second mode, basically. Okay? So the on because of the inductor. Okay? So what about the inductor voltage? So in this mode, the inductor voltage is nothing but the opposite of the output voltage. Okay, so in one mode, we are applying a positive voltage. In one mode, we are applying a negative voltage to the inductor, and on average, it is 0. Then we can find the voltage transfer ratio. Unfortunately, we are running out of time here. I'm going to continue this next time on Tuesday. All right, so see you guys on Tuesday.